So the next speaker is Alex Rebert from Google. And Alex brings hard-won industry experience in memory safety at scale. And at Google, and previously as co-founder of For All Secure, he has worked on large-scale vulnerability reduction and where architectural approaches like CHERI fit. So it's really great to be able to have Alex here. And thank you for coming. So, prefer the phone right now or?
Yeah, that works. Hey everyone, I'm Alex Rebert. I work at Google working on kind of transitioning Google to memory safety. And I admit when I got the invitation to Cherry Blossom, I was initially hesitant. I'm a software guy. So I hope you'll indulge me that maybe I'll talk a little bit more about software than the average talk today. But I hope the industry trend I'm going to talk about are going to be interesting. But I promise I will get to Cherry near the end. Let's take a step back and kind of set the scene. This is Jen. Oops. Here we go. This is Jen Usterly. She is a former director of CISA in the US, and she gave a speech at CMU a few years ago. And in that speech, she compared the tech industry of today to the car industry 60 years ago. Back then, there were a lot more car crashes, and we blamed the drivers. They went too fast, they weren't paying attention, and sometimes that was true. But it also turned out that some of the more popular models at the time had design flaws that made them susceptible to rollover on turns. We blame the drivers, but it was not always their fault. And I feel today in the tech industry, we do that too, where we blame developers for some of the memory safety bugs that are really, really hard to avoid. And I think what we realized over the past decade or two is that this is not a skill issue. It is pretty impossible to use C and C++ correctly. And so we have to stop blaming the developers, and we have to start building safer cars. And so the mandate really is a transition to security by design, especially in the context of memory safety. And for new code, the answer is clear. We should be using memory safe languages. This has been shown to work and remove most of the vulnerabilities. But of course, the question becomes, what do we do about the giant pile of C and C++ that we have running in production today? Probably billions of lines across the industry. How do we handle that? Retrofitting safety onto memory-unsafe languages is notoriously difficult. We've been trying for a quarter of a century or more, and we're still talking about it. We're still in this mess. And looking at the massive code bases across the industry, it felt like it was going to take decades, maybe till 2060, to get to a place where memory safety is not in the top 10, top 20 CWAs year after year. However, I think there's 3 changes that happened recently over the past few years that may actually change this timeline a little bit. The first thing that's changing this timeline is kind of some laws of software physics that I think we've recently discovered. And let's take Android as an example, because I work at Google. They've been transitioning new code to memory-safe languages since about 2019. There's always been some Java, but I think there's been a bigger focus in 2019 to kind of use Rust and Kotlin and Java for new code. And since then, the fraction of memory safety vulnerabilities that we've seen in Android has gone from the 70%, which is kind of the industry norm for C and C++ code bases, to 20%, which I think is an astonishing reduction in only 6 years. And they did that without rewriting most of their C and C++. And in fact, during that time, the memory-unsafe code base became bigger, even though the vulnerabilities kind of dropped. How is that possible? Well, it turns out that bugs have a half-life. They decay exponentially with time when code is exercised, running in production, tested. You can see in the graph the median lifetime is about 1,000 days, 2.5 years or something. Which means, if you were to stop writing new memory-unsafe code, except for fixing the bugs that you find, you would have only half the vulnerabilities that we have today in 2.5 years, which I think is a remarkable outcome, very counterintuitive to me. But what that means is that new code is where most of the risk is and where we should focus on. So the target area is a little smaller in terms of risk that we thought. Of course, not claiming that fixing new code is sufficient. There was an example from the previous keynote about a 32-year-old vulnerabilities. We still have to worry about that. But the second kind of further we're seeing is that spatial safety may be affordable. We may be able to retrofit spatial safety at scale onto C and C++ in a way that is less expensive than I thought. And part of the reason is that compilers and linkers are becoming really good at optimizing bounce checks. Part of that, I think, is some of the newer languages built on the same compiler platforms like LLVM have bounce checking, and so people have looked at them, optimized them. And this is especially the case when you use some more advanced optimizations like feedback-directed optimization, which can kind of move cold code away from the hub path. And so, as an example, we rolled out bounce checking across all of our server-side software for the C++ standard library. So now if you use a std vector, a std array, a std span, this will be bounce checks. We found thousands of bugs, which was very exciting. Hopefully this will make one of the barriers to adoption of CHERI that already Whitehouse mentioned, people finding new vulnerabilities. Hopefully we're cleaning some of those up. But the other thing that I think was remarkable is that it only cost us 0.3% of our field CPU. At Google scale, this is still a fair bit of CPUs, but this is a lot more affordable than we expected. This also requires some code modifications. For C, we have to annotate pointers using advanced safety. For C++, we have to make sure that all of the array accesses have a length-bearing type so that we can actually enable a bounce check. So this is not trivial, but we think this is actually automatable to a large extent. And this is what we're working on. And the last for us is perhaps the elephant in many rooms today is AI. I'm not here to hype up LLMs, but I don't know if you've used a coding agent over the past 6 months. They've gotten shockingly good. And this makes rewrites significantly cheaper than they used to. They're still expensive today. We're not going to rewrite the Keynote scale tomorrow with AI. But given the trajectory that we're seeing, it is possible, if not likely, that we will be able to rewrite a big chunk of our C and C++ relatively cheaply. And either way, we don't necessarily need AI to rewrite all of the software. If we think about kind of the first data on vulnerability decay, if we focus on the code that's actively being added or actively modified, that will take care of a big chunk of the risk. And so between vulnerability lifetimes, affordable bounce checking, and AI progress, the 2060 timeline may not be 2060 anymore. The risk from C and C++, I expect, will be shrinking at an accelerated pace, but exactly how fast is anyone's guess. And I do want to acknowledge that even if we had the capability to rewrite like everything to say Rust or whatever, not everyone will want that. People either like C and C++, maybe they won't have time to learn new languages, so there'll be some complex social dynamics there that will kind of prevent the diffusion of some of those things. Either way, let's say a server-grade, data center-grade CHERI chip hit the market in the 2030s. It is possible that the memory-unsafe problem will look a little bit different by then. But I think there will be two big gaps still standing. And the first one is going to be temporal safety. We think spatial safety may be solvable relatively cheaply, but I don't see that happening for use after free necessarily. One way to retrofit temporal safety on memory-unsafe code is to use something like garbage collection or reference count. But those come with a pretty heavy performance tax. Those are some early numbers from FieldC, which is pretty much like CHERI in software, as far as I understand. And especially with the cost of RAM today, garbage collection with maybe 50% memory overhead becomes quite expensive. The other way of solving temporal safety would be to do what Rust did. Rust is kind of an existence proof that we can do this at compile time with static lifetimes and exclusive mutability. Unfortunately, the C++ community rejected a pretty good proposal last year, and so this may not be happening for C++, but I hope they'll reconsider that. The other massive gap is the supply chain. So we may be able to migrate some of the code that we own, the people that have sufficient abilities to do that and are willing to invest. But we won't be able to migrate code that we get from the open source communities or from vendors to safety necessarily. Think of the firmware in the hardware that we buy, or some of the RSS projects. And this is a famous XKCD comic about the supply chain. That random person in Nebraska may now be interested in learning about the new memory-safe language, about bounce checking, and they may not have any more of their volunteer time to invest in that project, which is a very reasonable stance for them to take, but it does leave a pretty big gap in terms of memory safety. And that gap is probably going to actually increase in the short term, at least because of AI being surprisingly good at finding vulnerabilities now. And to previous keynote again, there's probably going to be a flood of vulnerabilities coming our way because of that. And so if some of the risks from C and C++ are expected to shrink, at least after we get past the initial wave of vulnerabilities from AI, what does that mean for CHERI? And I think the answer depends a little bit on the trajectory of AI. And I was discussing with Robert Watson a little bit about different hypotheses of how capable those systems may be. And I want to talk about maybe two possible futures and talk about CHERI's role in both. In the first world, AI doesn't progress quite as quickly as it has perhaps it levels off. Either way, we're not able to rewrite a big chunk of our memory-unsafe code. And in that world, companies that are willing to invest will continue to harden their code, maybe advanced checking where they can, but mass-code rewrites is out of reach. Here, CHERI can provide special safety to the code that we can fix. It may also even provide some protection against temporal safety bugs, if only due to the referential safety, right? Preventing the mixing of data and pointers is super promising. But I think in this world, we may still hit this temporal safety performance issue. The early prototypes built on top of CHERI are really exciting, but they're built on memory scanning at the moment, and I think the performance hit from that is something that will be hard to afford. And so if I had one wish I could make today, it would be to keep pushing on temporal safety. I know there's exciting research on the pipeline, and I think we'll need one or two breakthroughs in that space to make it work at scale. And I expect some of those breakthroughs will need to be at the architecture level. And CHERI is a great place for that. And so let's imagine a second world now where AI keeps on this super fast trajectory and is able to rewrite a big chunk of our C and C++. Here, I think the value proposition from CHERI may change a little bit. I think it will be less about providing memory safety to this vast amount of legacy code, but I think it will be more about protecting some of the more sensitive code bases that perhaps we won't be able to rewrite because they're more tricky, or that will rely more on unsafe code still. And JITs come to mind, right? People are mentioning Chrome before. If we write V8 in Rust, let's say, we still are writing actual instructions in V8 that may not be protected by that. And CHERI can come in there really well, as well as language runtimes. Then we have OSs and firmwares, things that are kind of like close to the metal, having to interact with hardware, where we can use language level safety properties to protect. And then the last one is we'll likely still have some memory unsafe code, perhaps some projects that are just too complicated to migrate, and then the sandboxing and compartmentalization would be really helpful here, in addition to kind of the supply chain attacks that we are seeing. And something I also want to mention about this world is like memory safety is a 50-year-old problem. We've tried a lot of things, right? And nothing really has worked that well. And so like I don't think we should necessarily bet on one single bullet, silver bullet. Like AI will solve all of our problems. I think we're going to need a portfolio of approaches to make sure we actually tackle this in the next 10 to 20 years. Oh, that was my talk. Thank you so much for having me, and I'm happy to take questions.
We already have questions.
So yeah, a couple of things on the exponential decay of memory safety bugs. I think the first thing is that that's a statistical defense, and you know, exponents never get to zero. You have to fix all your memory safety bugs to actually be secure. And I think the second thing is that, you know, what we've seen historically is that exponential curve is true for bugs that we know how to find. But then we find a new class of bugs, and then suddenly we're back up to all of the old code with a ton of bugs in it. I just wanted to mention those two things.
Yeah, and I'm very interested to see, you know, this graph I showed in 5 years after we have AI finding perhaps a bunch of new vulnerabilities that have been kind of here in the code base for a long time. And it's possible that when there's new technique discovered or new bug classes, we'll see a spike before the
Okay, other question?
What was it that you had said about profiles? I just want to clarify that really quick.
Yeah, what we've seen is that the overhead from bounce checking is reduced significantly when you enable profile-guided optimizations.
Sorry, I mean C++ profiles, because you made some claims about it. I'd like to. I wasn't quite sure what you said.
Yes. So last year there were kind of two proposals for the C++ committee.
Yes.
One was the Safe C++ proposal that had lifetimes. This was rejected. So they are going with profiles, which is, I think, a subset of the language that's supposed to provide memory safety. I am not quite clear how temporal safety is going to be provided in this model.
Yes, it's certainly not perfect. I just wanted to clarify that. But I wish you had mentioned that the C++ 26 standard is adding library hardening to the language as a standard feature of it. So yes, bounds checking doesn't solve everything, but we are making progress in that direction. I can also speak to a little bit why Safe C++, the proposal was rejected. If you're interested, I am on the committee. In case you were wondering why I know about this, I just would like to say that over there we do take safety seriously there as well, and we're making progress there. I don't think C and C++ should be conflated. They're two very different languages, and they should be separated.
Yep, that's a fair point. I would love to chat with you
Sounds
afterwards.
good. And thank you for the talk.
Thank you. Other questions? Okay, if not, I can ask a question maybe. You showed the infrastructure of the internet, our digital life, relying on one pillar that is very, very tiny. What about supply chain attacks? We hear a lot about open source repositories being poisoned by malicious actors who intentionally include problems, vulnerabilities in there. So I guess that's a real concern, isn't it?
Yeah. I mean, that's a huge concern. We're seeing multiple attacks. Right? There was one recent one, I think, this week in Python, like LLM, which was compromised. We actually expect this to become worse. We're worried that the flood of vulnerabilities due to AI is going to burn out many maintainers. We've seen that in the XZ attack, right? They kind of relied on the maintainers being overburdened, not having enough time, and then to pressure them to give ownership of their repo, and that's how the attack happened. And I think all the maintainers will become more susceptible to this. In terms of defenses, this is tough. Because of the flood vulnerabilities, we'll want to be patching faster, right? If AI attackers can find and exploit vulnerabilities in hours of days, that means that we have to import new versions and updates and patches really quickly and make them available to production. And that means we have actually less time to review the code that we import from upstream to make sure it was not compromised. And so this is a huge problem. It's probably going to get worse. And I don't think we have great solutions at the moment to protect us against that. Manually reviewing all of the code that we import from a giant open source dependencies, I don't think it's practical for most people, for most developers or businesses. That's what we try to do at Google, right? But that's a huge amount of time.
Okay. So that's why we need more security by design, right?
Absolutely.
Yeah, just advertising for CHERI. Sorry. Other questions in the room? No? Okay. So thank you again. Thank you for your participation and a really interesting discussion.
Thank you.